Conceptual Introduction, the Gaussian Method. Welcome, everyone. Today, we are beginning a new subsection where we will explore the intuitive logic behind a very clever mathematical shortcut. Specifically, we are going to learn how to calculate the sum of a sequence of numbers without the tedious task of adding them one by one. This method is named after the famous mathematician Carl Friedrich Gauss. Legend has it that he discovered this brilliant technique all the way back when he was just a young schoolboy, and today, we are going to walk through that same logic to see how it works. The problem. Now that we've introduced the concept and the story behind the Gaussian method, let's look at a concrete problem to see why we actually need this technique. Imagine you are faced with a task. You are asked to find the sum of all positive integers starting from 1 all the way up to 100. If you were to use the traditional standard method, you would simply add them one by one in order. You would write it out as s equals 1 plus 2 plus 3 plus 4 and so on, continuing through 99 and finally adding 100. Now, while this approach is mathematically perfectly correct, think about the practical side. Doing this by hand is incredibly time-consuming, and the longer the list of numbers, the more likely you are to make a small calculation error that ruins the whole result. However, as we'll see in the next few slides, the great mathematician Gauss realized that there is a hidden pattern within these numbers, a pattern that allows us to bypass all that tedious addition and find the total much, much faster. The Gaussian logic, step by step. Now that we understand the problem we are trying to solve, let's dive into the actual logic behind the Gaussian method. The core idea here is quite brilliant. Instead of adding numbers one by one, we are going to pair numbers from the very beginning of our sequence with numbers from the very end. By doing this, we aim to create constant sums, meaning every pair we create will add up to the exact same value. To get started, let's follow a step-by-step process. Step 1 is simply to write out our sum in its original ascending order. To keep our work organized, let's use the letter S to represent the total sum we are looking for. So we write S equals 1 plus 2 plus 3 and so on, continuing through 98, 99, all the way up to 100. The Gaussian logic, step by step, continued. Now that we have our original sum written out from 1 to 100, let's move on to step 2. We are going to write the exact same sum, S, but this time, we'll write it in reverse order. You might be wondering why we are doing this, but it relies on a fundamental rule of mathematics, the commutative property of addition. This property simply tells us that when we are adding numbers, the order in which we add them does not change the final result. So, instead of starting with the smallest number, we will start our sequence with the largest number and work our way down. This means our sum, S, can also be expressed as 100, plus 99, plus 98, and so on, all the way down to 3, 2, and finally 1. By doing this, we are setting ourselves up for the next step, where we will actually stack these two different versions of the sum on top of each other to reveal a very clever pattern. The Gaussian logic, step by step, continued. Now that we have our original sequence and our reverse sequence written down, we move on to step 3, which is to add these two sequences termwise. To find the magic pattern, we are going to add these two equations together vertically. We align the first term of the first sequence with the first term of the second sequence, the second term with the second, and so on. Think back to what we did in the previous slides. We have the sum, let's call it S, starting from 1 and going up to 100. Then, we wrote that same sum S again, but this time, we reversed the order, starting from 100 and counting all the way down to 1. When we add the two S's together, we get 2S, which we write as 2S on the right side of the equation. Look at what happens when we group them. The first pair is 1 plus 100, the second pair is 2 plus 99, the third pair is 3 plus 98, and this continues all the way to the final pair, which is 100 plus 1. As you can see, we are essentially pairing the smallest numbers with the largest numbers. This leads us directly into our next step, where we will observe something very interesting about the value of these pairs. The Gaussian logic, step by step, continued. Now that we have added our two sequences together, let's move on to step 4, where we observe the constant sum. If you look closely at the pairs we just created in the previous step, you will notice something very important. Every single pair adds up to the exact same value. For instance, 1 plus 100 equals 101. Similarly, 2 plus 99 equals 101. And 3 plus 98 also equals 101. This pattern continues all the way through the sequence. This consistency is the magic of the Gaussian method, as it shows us that we aren't just adding random numbers, but rather a series of identical sums. The Gaussian logic, step by step, continued. Now that we have observed that every pair adds up to the same value, we move on to the final step, calculating the total. Take a look at what we have achieved so far. Since we are working with a sequence of numbers from 1 to 100, we have exactly 100 numbers in our list. Because we added the sequence to its reverse, we have created 100 of these pairs, and as we saw in the previous slide, each of these pairs equals 101. This means that 2 times s equals 100 multiplied by 101. When we perform that multiplication, we find that 2 times s equals 10,100. However, remember that this value represents 2 copies of our sum, the original sequence and the reversed one. To find the value of a single s, we must divide this total by 2. So, we set up our calculation as s equals 100 times 101, all over 2. To make this easier to solve mentally, we can divide the 100 by 2 first, which gives us 50. Now we simply multiply 50 by 101, which brings us to our final, beautiful result, 50/50. It is much more efficient than adding every number one by one, isn't it? Real-world analogy, the balanced scale. Now, to help you truly internalize this concept, let's step away from the numbers for a moment and look at a real-world analogy, the balanced scale. Imagine you have a traditional balance scale. Suppose you have a set of weights that increase linearly, much like the sequence we just worked through, starting with 1 kilogram, then 2 kilograms, 3 kilograms, and so on. If you take the lightest weight, which is 1 kilogram, and pair it with the heaviest weight in your set, you create a specific, balanced weight. By consistently pairing the lightest remaining weight with the heaviest remaining weight, you are essentially creating a standard unit of weight that stays the same for every pair. Just as we saw with the numbers 1 through 100, where every pair added up to 101, this method allows us to take a complex, long addition problem and transform it into a much simpler multiplication problem. As we will see in our final summary, this is the secret to the efficiency of the Gaussian method. Key takeaways. First, let's look at the pairing strategy. As we saw in the previous slides, the secret to this method is not adding numbers one by one, but rather pairing them up. You can find the sum of a linear sequence by pairing the very first term with the very last term, then the second term with the second to last term, and continuing this pattern until you reach the middle. Second, we have the concept of the constant sum. This is a crucial observation from our calculation. In an arithmetic progression, which is just a fancy way of saying a sequence that increases by a steady amount, the sum of these pairs will always be the same value. Whether it is 1 plus 100 or 2 plus 99, the result remains constant. Finally, let's talk about efficiency. The real power of the Gaussian method is that it transforms a long, exhausting addition process into a much simpler multiplication and division task. If you can identify the number of terms, the first term, and the last term, you can use this formula. The sum equals the number of terms, multiplied by the quantity of the first term plus the last term, all divided by 2. Now that we have walked through the step-by-step logic of how Gauss achieved this, let's summarize the key takeaways from today's lesson so you can apply this to any similar problem. As we move to our final slide, I want you to keep a close eye on a few common pitfalls that students often encounter when using this formula. Common mistakes. First, let's talk about the most frequent mistake, forgetting to divide by 2. Remember, in step 5 of our derivation, when we added the two sequences together, we weren't just calculating the sum s. We were actually calculating 2 times s. Because we used both the original sequence and the reverse sequence, we essentially created 2 copies of the total sum. If you simply multiply the number of terms by the pair sum, you'll end up with a result that is exactly double what it should be. So, always make it a habit to perform that final division by 2 to get back to your single sum. Second, be very careful not to miscount the number of terms in your sequence. It sounds simple, but it is easy to lose track, especially when a sequence doesn't start at 1. As we saw in our example, when we add a sequence of n terms to its reverse, we end up with n pairs. If you miscount how many numbers are in your list, your entire multiplication will be off. Always double-check your count of the terms before you proceed with the calculation. Now, before we wrap up today's lesson, I want to touch on a few common pitfalls. Even when you understand the logic of the Gaussian method, it is very easy to make small clerical errors that can lead to the wrong answer. Keep these 2 points in mind, and you'll be able to apply this method with much greater accuracy.